Hello everyone, welcome to Brain Blitz Audios. Today in this episode of NEET Preparation, we'll be looking at previous year questions of physics in medical entrance examinations in India. Today we'll be dealing with the chapter Moving Charges and Magnetism. It is the fourth chapter in the grade 12 syllabus for physics in CBSE. Let's jump right into our first question. An electron is traveling along the x direction. It encounters a magnetic field in the y direction. Its subsequent motion will be a straight line along the x direction, b a circle in the xz plane, c a circle in the yz plane, d a circle in the xy plane. So when a charged particle is passing through a magnetic field, is undergoing motion through a magnetic field, then one of three cases happen. One, when theta is equal to 0, the particle passes in a straight line. When theta is greater than 0 degrees but less than 90 degrees, then it follows a helical path. And when theta is equal to 90 degrees with respect to the magnetic field, then it goes in a circular path. Let's look at our question. The electron is passing in the x direction. So this is our electron. And a magnetic field is induced in the y direction. Let's consider this as y. So as you can see, the magnetic field is perpendicular to the motion of the charged particle. So theta is equal to 90 degrees. So it will form a circular path, and this circular path will be perpendicular to the direction of the magnetic field. So the plane which is perpendicular to the y-axis is the xz plane. So therefore, option B, circle in the xz plane, is the right answer. Option A, straight line along the x direction, is incorrect. That happens when the magnetic field is also along the x direction. For a circle to occur in the yz plane, the magnetic field has to be in the direction of the x-axis, and for a circle in the xy plane, the magnetic field will have to be in the direction of the z-axis. So that's why option C and option D are incorrect. In our case, when magnetic field is passing along the y direction, then the circular path forms on the xz plane. That's why option B is the right option. Next question. A rectangular loop carrying a current I1 is situated near a long street wire carrying a steady current I2. The wire is parallel to one of the sides of the loop and is in the plane of the loop as shown in the figure. Then the current loop will A, move away from the wire, B, move towards the wire, C, remain stationary, and D, rotate about an axis parallel to the wire. So in order to do this question, we need to look at the forces that act between two parallel straight line conductors. So between two current carrying parallel conductors, the force that is between them is A, proportional to the inverse of distance, so it's inversely proportional to distance, and the force is also dependent on the direction of I1 and I2. So let's redraw the diagram right here. So we have a straight conductor with current I2, and we have a coil. Let's christen it ABCD. And the current that's flowing through it is clockwise, and the current is known as I1. Now, For arm AB, you see that current I1 is parallel to current I2. They're both flowing in the same direction. So therefore, we have attraction in this case. So the arm of the loop and the straight conductor starts to attract each other. For the arm BC, for the arm CD, you notice that the current is flowing in the exact opposite direction in the loop as compared to the straight line wire. I1 is flowing in minus K direction, I2 is flowing in plus K direction, for example. So therefore, when current flows opposite, then there will be a repulsion between them. And as for the force experienced by the arms BC and AD of the loop, they get cancelled due to each other. Force due to BC is cancelled by force due to AD. So no effect whatsoever. Now remember, we said that this magnetic force is inversely proportional to displacement. If you notice in the loop, AB has a shorter distance R than CD, which has, say, a combined distance of R plus D, supposing D is this distance. So as you can see, there is a greater distance that separates arm CD from the straight conductor, so it will have less force. So force due to CD will be less than force due to AB. So therefore, since AB is intending to be attractive towards the conductor and CD is tending to be repulsive, we can say that the overall effect would be one of general attraction. So therefore, option B, move towards the wire, is the right option. Option A, move away from the wire, will be true when the current flows anti-clockwise. So it is incorrect. And in this situation, current doesn't usually remain stationary because of the movement, because of the force due to the magnetic field of the two current carrying parallel conductors. And option D, rotate about an axis parallel to the wire, is also incorrect. Now, let's look at this question. The cyclotron frequency of an electron gyrating in a magnetic field of 1 Tesla is approximately 28 megahertz, 280 megahertz, 2.8 megahertz, 28 gigahertz. Now, this question is an ideal situation because in most cases, cyclotrons never accelerate electrons because there is a problem in synchronization when an electron is accelerated in a cyclotron. So this is an ideal situation. It does not happen in real life. Having said that, let's move on to the question. So the quantities given are for an electron, the charge always remains 1.6 into 10 raised to minus 19 coulombs, and the mass always remains 9.1 into 10 raised to minus 31 kg. And we're given the magnetic field here, which is 1 Tesla. So gyration refers to circular motion. So in effect, what we have is an electron moving in a circular path in a magnetic field. So when a charged particle moves in a circular path in a magnetic field, then its magnetic force will be equal to the centripetal force required for the circular motion. So therefore, mv squared by r will be equal to qvb. So one of the v's gets cancelled, so mv by r will be equal to qb. Let's take m to the right hand side, so we have v by r is equal to qb divided by m. So let's keep this aside as equation 1, and let's look at the circular motion in itself. So In circular motion, the velocity of the particle v will be equal to distance, which is the circumference, that is 2 pi r, divided by the total time period t. So we'll get the time period in this scenario as 2 pi r divided by v. Now, the question is asking us to find frequency. So frequency is 1 by time period. So that'll be equal to v by 2 pi r. So that is what we should be calculating. So let's calculate the frequency, and let's give it a symbol, say n. So n is equal to v by r times 1 by 2 pi. So let's put in the value of v by r as qb by m. So it'll be qb divided by 2 pi m. So we know the charge of the electron, we know the mass of the electron, we know the magnetic field. Now let's apply them. So Q is 1.6 into 10 raised to minus 19 coulombs times 1 Tesla divided by 2 pi times 9.1 into 10 raised to minus 31. So now what we do is we take 10 raised to minus 31 to the numerator, so that becomes 10 raised to 31 plus 31. So 10 raised to 31 minus 19 will give you the value of n as 1.6 into 10 raised to 31 minus 19. So 11 minus 9 is 2. 2 minus 1 is 1. So it's 10 raised to 12 times 1 will be the same. So divided by 2 pi into 9.1. So we know that 8 times 2 is 16. So 0.8 times 2 will be equal to 1.6. So we can cancel 2 from the denominator. So we'll get 0.8 into 10 raised to 12 divided by 9.1 pi. So let's multiply 10 on both the numerator and the denominator so that there is no change. So we'll get 8 divided by 91 pi into 10 raised to 12. So let's find out 91 pi. So we'll put the value of pi as 3.14. So it'll be 8 by 91 times 3.14 into 10 raised to 12. So let's multiply 314 by 91. So that'll be 314. 4 times 9 is 36. 1 times 9 is 9. 9 plus 3 is 12. 3 times 9 is 27. 27 plus 1, 28. 4 plus 0 is 4. 1 plus 6 is 7. 3 plus 2 is 5. And then we have a 28. So we will have n is equal to 8 divided by 285.74 into 10 raised to 12. Let's multiply both sides by 100, both the numerator and denominator by 100. So we'll get 800 divided by 28574 into 10 raised to 12. That is equal to 8 divided by 28574 into 10 raised to 14. So now we can take 2 common from both ends and cancel it. So dividing both sides by 2. So 8 by 2 will give you 4. And divided by, let's take 28574 and 2, 28, that's 14, 28, 0, and then 5. So 2 times 2 is 4, and that's 1. And we have 17, so 8. 2 times 8 is 16, so that's 1. and then 14. So 2 times 7 is 14, equal to 0. So 4 divided by 14287 into 10 raised to 14. In order to make our calculation simpler, let's make 4 as 40,000. So it'll be 40,000 divided by 14287 into 10 raised to 14 minus 4 will be 14 minus 5 will be equal to 9. So 4 into 10 raised to 14 will be the same as 40,000 into 10 raised to 9. So let's now divide 40,000 divided by 14287. So 14287 times 2 is 28574. Let's look at what 14287 times 3 looks like. 7 plus 4 is 11. 8 plus 8 is 16. 6 plus 2 is 8. 8 plus 4 is 12. And then we have 4. So 14287 times 3 is 42861, which is greater than 40,000. So let's stop with 2. So it'll be 28574. And 10 minus 4 is 6. 10 minus 7, 9 minus 7 is 2. 9 minus 5 is 4. 9 minus 8 is 1. 3 minus 2 is 1. So we have 11426, which is lesser than the divisor. So we'll multiply a 0 here. So it becomes 14287 times 8 will fit in here. So that will be equal to 114,096. Again, 10 minus 6 is 4. 15 minus 9 is 6. And then 1 minus 0 is 1. 4 minus 4 is 0. And then 0 and then 0. So we have a small remainder of 164. And the quotient we got as 28. So it'll be 28 into 10 raised to 9 hertz, which is the unit of frequency. Now 1 gigahertz is equal to 10 raised to 9 hertz. So we can write this sum as 28 GHz. 28 gigahertz is the frequency of this cyclotron, of this electron. So therefore, option D, 28 gigahertz, is the right answer. All of the others are in the range of megahertz. So it will be 10 in the order of 10 raised to 6, but we got the order of 10 raised to 9. Now let's look at the next question. Magnetic moment of a current carrying circular coil of radius r and number of turns varies as. So we need to know the formula for the magnetic moment of current carrying circular coil of radius r and number of turns n. So the magnetic moment has the formula I times A, and since this circular coil has number of turns n, then it will be IA times n. So that is the formula for magnetic moment of current carrying circular coil of conductor. So the area here represents the area of the coil. And since the coil is circular, which has a radius r, the area of the coil will be equal to pi r square. So it'll be n times I times pi r square, Ni pi r square. So as you can see, the magnetic moment will have a direct relation with r, the square of r. So therefore, option D will give you the right option, which is r square. So the magnetic moment is proportional to r square because of the fact that the formula for magnetic moment is Ni times pi r square, where pi r square is the area of the circular coil. Let's look at this question. A circular coil of radius capital R carries an electric current. The magnetic field due to the coil at a point on the axis of the coil, located at a distance small r from the center of the coil, such that small r is way greater than capital R, varies as. So for this, we need to know the magnetic field on the axis of the coil. Magnetic field on the axis of the coil, B is equal to 1 by 4 pi epsilon naught Ni times pi capital R square. So this is magnetic moment divided by R square plus capital R square, the whole raised to 3 by 2. So this situation is something like this. So we have a coil here and we have to find the magnetic field at some point P, which is some distance small r away, and the radius of the coil is capital R. So we know that this point P is very, very far away from the coil. So that small r is way greater than capital R. So when small r is way greater than capital R, we ignore capital R in the denominator in this formula. So the formula B will now turn out to be B is equal to 1 by 4 pi epsilon naught Ni pi capital R square divided by only small r square in the denominator times 3 by 2. 2 and 2 gets canceled. So the magnetic field B is proportional to 1 by r cubed. Therefore, option D is the right option because there's a square inside the bracket and there's a 3 by 2 outside. So that both the 2's gets canceled because we can do exponents the same way we do fractions and stuff. So we'll get small r the whole cube as the order of the displacement between the point and the circular coil along the axis of the center. So B is proportional to 1 by capital R cubed. Now, let's look at our final question of this episode. The magnetic field due to a straight conductor of uniform cross-section of radius A and carrying a steady current is represented by. So we have a straight conductor like this. So the cross-section has a radius A, and we have, say, a point outside and inside it. So let's keep these distances as the quantity small r. So we need to find out how is the magnetic field represented in a graph. So for a magnetic field inside a wire of these dimensions, it'll be equal to mu naught times J R divided by 2, where J is current density. And for outside the wire, B will be equal to mu naught J capital A square divided by 2R. So these two formulas are obtained from Ampere's circuital law using J, that is current density. So in both of these cases, for field inside the wire, let's write it down here somewhere. So for the field inside is proportional to the distance of the point, which is B is proportional to R. But once it goes outside, the point goes outside the wire, then B is inversely proportional to R. So when B is directly proportional, we get a straight line. And when B is inversely proportional, we get a rectangular parabola. So in a graph like this, so till the point A from the origin till the point A, the graph varies linearly, and then it reaches its highest point, and then it starts going downward with a rectangular parabola. So this is the condition of the graph in this situation. And the graph here that shows you the correct representation is graph A. In graph B, it is said that the magnetic field inside the wire is constant, which is not true. And in graph C, it's said that the deceleration, the decrease, is also given in a straight line. So what this part means is that B is proportional to minus R, which is not the case. Option C is incorrect. And option D states that there is no such thing as a magnetic field inside a straight conductor. That's why there is no line here, and the line starts from A onwards, which is also incorrect. The right answer is option A. This half gives the relation that B is proportional to R, and this half gives the relation that B is inversely proportional to R once it goes over the threshold of the radius of the conductor. And that's why option A is the right option. And that concludes this webisode of NEET preparation. We have a lot of episodes on NEET preparation, so we'll provide the playlist in the description down below. Don't forget to click on it and look at our other videos and view them at your leisure. So for accessing more of our useful and interesting content, you can subscribe to our channel, Brain Blitz Audios, and you can also hit the bell icon, the notifications button, for receiving the latest of our most useful and interesting content, such as memory hacks, mind maps, learner words, etc. Until the next episode, take care, stay safe, bye-bye for now.